I'm Johnson J. Bugo, and this is our project for linear algebra. For our 3D object, we chose cube and we created a 3D transformation program using HTML, CSS, and JavaScript. Our program demonstrates the four basic transformations from linear algebra: translation, rotation, scaling, and reflection. This program shows the cube transformed in real time using 4x4 matrices. This is our program. On the left, you can see the cube drawn on the canvas. On the right side, we added sliders and buttons to control the transformations. When I move these sliders, the cube updates immediately because the script applies transformation matrices every frame. The cube is represented as 8 points in 3D spaces, and edges connect these points to form a wireframe. So this is for the side, up, and for the depth. You can really see that. Rotation, rotate Y, rotate Z, and this is for scaling. As you can see, wait, there you go. Reflections invert this side to this side. So basically just inverts this commands and rotations. So in translation matrix derivation, translation moves the objects by adding tx, ty, and tz. To get tx, ty, and tz, you have x equals x plus tx and y equals y plus ty and z equals z plus tz. So this will be what should it look in a 4 by 4 matrix. Multiplied with a point x, y, z, 1. So 1 times x plus 0.0 times y plus 0 times z plus tx times 1. In y, where it's y times y, 1 times y plus ty. Z will be 1 times z plus tz. W will be just 1. So, scaling. Okay. Uniform scaling changes each coordinate by a single factor s. So, x equals s times y, s times x, s times y equals y, z equals s times z. This will be the matrix and stretches or shrinks the cube around the origin. Rotation matrices. Rotation uses trigonometry based on the unit circle. Rotation around x-axis, y and z changes. So, imagine projecting a point onto a yz plane. We rotate it using cosine and sine. This will be the matrix. For this, y equals y times cosine minus z times sin. And z will be y times sin plus z times cosine. Now, onto now onto rotation around y-axis, x and z change. So this will be x equals x times cosine plus z times sin. Then z will be negative x times sin plus z times cosine. This will be our matrix. Or for the rotation of z-axis, x and y change. For this, x is equals to x cosine minus y times sin. And y is equals to x times sin plus y times cosine. This will be the matrix. And on reflection flips a coordinate. So if it's x becomes negative x, y becomes negative y, z becomes negative z. This will be an example on as a matrix. How how they apply to the object. Each frame, I multiply these matrices together and apply them to every point of the cube. Metric multiplications transforms the entire cube into one calculations. Projections. How 3D becomes 2D. The cube is 3D but the canvas is 2D. I simulate a simple projection by screen x equals x plus center x and screen y equals y plus center y. This is called orthographic projection. It ignores the perspective, making the math simpler. This lets us see the cube on the screen after transforming it. In summary, my project uses 4x4 homogeneous transformation matrices to apply translation, rotation, scaling, and reflection to a 3D cube. Each frame, the program composes these matrices into one final matrix and multiplies it by every point of the cube. This shows how linear algebra powers real 3D graphics. Now, I will explain how the code works. Matrix for class. This it. This part stores a 4x4 matrix and allows matrix multiplication. This part, this whole section, this is the core. It it also has a function transform point. This, which multiplies a point by the matrix. This is our core for the math for this program. This part. Now, for our transformation matrix, we created functions like translate, scale, rotate x, rotate y, rotate z, and reflect. There it is. Translate, scale, rotate x, rotate y, rotate z, and reflect. Yeah, this is for reflection. Each function returns a 4x4 matrix based on a formula I showed earlier. The formula, just like the last time I show you in the notepad. Now, for the next part is for building the final matrix. Inside the draw function, cube definitions. The cube is made out of 8 3D points. That represents its corners. I store these points in a list, and then I have another list called edges, which tells the program which corners to connect to from the wireframe cube. Next will be our drawing part. In the drawing function, each point is transformed using the matrix I built from all the sliders. Then, I convert the 3D coordinates into 2D screen coordinates. Then, draw lines between the lines that points based on the edges list. This creates the rotating and transforming cube we see on the screen. This project uses HTML and CSS to create a web interference for demonstrating 3D linear transformation. The HTML sets up the structure, including a canvas where a 3D object is drawn, and a control panel where sliders and buttons for translation, rotation, scaling, and reflection. Each controls updates the object position, orientation, or size in real time. The CCS style, the layout for clarity and usability. It uses flexbox to arrange the canvas and controls side by side. Adds padding, borders, and shadows for a clean appearance, and ensures sliders and field sheets are easy to read and interact with. In short, the HTML defines the structure and the CSS handles the appearance. And this combination creates an interactive platform for exploring our project. Transformation in action. Translation. Mm, Up, side, up, down, and for depth, it's with depth. For the rotation, the cube rotates smoothly along each axis. For rotate X, for rotate Y, for rotate Z, for reflections, this flips the cubes like a mirror depending on the axis. And for scaling, it's making it scale big and small. Now, in conclusion, in this project, I implemented the 4 main linear algebra transformation using 4x4 matrices, and I showed how they affect a 3D object. Thank you for watching. Hey, wait, no.